So, definition of countability, a set E is said to be countably infinite if if it is equicardinal with n, the set of natural numbers. So, as I just said, there are bigger infinities and smaller infinities, right. So, so if your set is as big as the set of natural numbers, meaning that there exists a bijection between the set you are considering E and the natural numbers, then the set E is said to be countably infinite. Okay. The definition clear? So, we just means, so if you want to establish that some set E given to you is countable, what will you do? Go and find a bijection between E and n, right. If you succeed, it is, even if you find one bijection, it is definitely countable, countably infinite, right. And a related definition, a set is countable if it is either finite or countably infinite. Okay. So, if a set is either finite, we all understand finite sets, it is either a finite set or a countably infinite set, we just speak of it as a countable set. So, there is a bijection from E to n. So, if the elements of E can be written as E1, E2 dot dot dot, correct. So, the moment you give me a natural number n, I can identify the element E n uniquely, and you give me an element, I can identify the index n, and this is true for real even numbers, right. So, for example, you can show that, so it is clear. So, if the moment you can put this in a list, right, it is a countably infinite set. So, I do not see, I want to make this very clear. This has, so the fact that I think the confusion is because the even numbers are a subset of the natural numbers, but still they are equicardinal, okay, because there is a bijection. You see the bijection. So, I mean if you take the even numbers, which is 2, 4, 6, 8 and so on, right. So, this is like 2n, right, where n is running over the natural numbers, and clearly that is a bijection, right. So, even numbers, so this is even numbers are equicardinal with n, and therefore, they are countably infinite, correct. This is clear. Never mind that this is contained in n, but they are equal in size because there is a bijection. Similarly, odd numbers are also in bijection with natural numbers, okay. What you can also show is all prime numbers are countably infinite, because you can identify the ith prime number. If I tell you what the 27th prime number is, you go and find out, right. So, in prime numbers are a countably infinite set, correct.
They can be indexed.
Yeah, if they can be put into a list, which is means that with natural numbers, right. If you can, what is a bijection after all? So, you have the natural numbers 1, 2, 3 blah blah blah, and you write the set in a list, and if all elements get covered, there is a unique association between every natural number and that element, and vice versa, right, correct. So, in that case it is a countably infinite set, okay. So, if you take the set of all integers, for example, let us say you take the z, right, z, which is 0 plus 1 minus 1 plus 2 minus 2 plus 3 minus 3 and so on, right. This is also countable, right. It is a countably infinite set. You may now argue that, well, this Z seems to have twice as many elements as natural numbers, right, because for every natural number there is a minus, right. So, you may, it seems tempting to say that this has twice as many elements as the natural numbers. No, not true. It only has as many elements as the natural numbers, because there is a bijection, right. You are convinced that this is a bijection. Every integer is contained here. You come up with an integer that is contained here and it is present in that unique spot, unique index. So, for every integer I can assign a natural number index, right.
Say for example, I am taking the union of a countably infinite set and a finite set. Say for example, a set of just single element irrational number. So does that become uncountable?
We will get to that. You are jumping ahead of me. Okay. But you understand what I mean here, right? So you are asking a question that I have not yet come to. Okay, taking union of countable sets. But this is okay. So Z is everybody convinced? So if you find a bijection, it is equicardinal. Okay, there is no other definition. Do not think of it as, oh, one is a subset of the other, so the other must be bigger or some such thing. They are equicardinal if there is a bijection. End of story.
If you replace natural number with any count in the definition, if you replace natural number with any countably infinite set, it will still make sense.
No, the concept of a countably infinite set is defined like this. It is equivalent. For example, you can equivalently define it with Z also. There is nothing wrong in doing that, but this is the standard definition. Okay, you can say equicardinal with Z also. There is nothing wrong with that, but we will stick to N. That is the standard notation. Okay. Any other questions? Okay, so far okay. Now what is, so this stuff must be very apparent to you. Okay. Now what is not apparent at all, and a lot of people find very surprising, is that the set of rationals is also a countable infinity. Okay, the set of all rational numbers Q, right, the fractions, right, P over Q where Q is not 0, the set of all rational numbers is also countable. Okay. So that seems very surprising in the beginning, because if I give you any two integers, let us say 21 and 22, there seems to be so many rationals just between these two integers, right. It seems to be a hopelessly large number. There are so many more rationals, it looks like, right. See, after all integers are rationals, all natural numbers are in fact rationals, and there are so many more rationals, an infinite number of rationals between any two integers, correct. So it seems like the set of rational numbers must be a much larger infinity than this n, right, but no, it is not. Okay. There are only as many rational numbers as there are natural numbers or integers, okay, which is quite surprising, right. Now how do you prove this? How do you prove anything is countable? Find a bijection. So if you find a bijection from, so somebody managed to find a bijection, so we are asserting that Q is countable, Q is countably infinite, right. So another example. So let us just consider rationals in rationals between 0 and 1. Okay. I will prove that rationals are countable a little bit later. So these are rationals in a countable set, right. What do you have to do? It is always the same thing, there is no different, every time you have to prove that something is countable, you have to find you have to either say it is a finite set, in which case there is no problem at all, or you have to prove that there is a bijection with natural numbers. You have to put the set in a list and the set should be finished, covered, right, that is all you have to do. So, how do you prove that rationals in 0 1 is a countable set? Find a bijection, right. So, here is a bijection. You write 1 by 2, well maybe you can put a 0 here if you want, okay, if let us be done with 0 first. 0 1 1 by 2, then you put 1 by 3, 2 by 3, okay. So, I am increasing the denominators, then I do 1 by 4. Now, I do not do 2 by 4 because it is already there, 2 by 4 is half, right. Then I would put 3 by 4, 4 by 4 is already there 1, right, and then 1 by 5, 2 by 5, 3 by 5, 4 by 5 and so on and so forth, right. 5 by 5 is already there, then I have 1 by 6, 2 by 6 is already there, 3 by 6 is already there, 4 by 6 is already there, then 5 by 6 and so on, okay. I am only so now all you have to show that this listing. So, I am listing this set out, right, you see what I am doing, right, I am increasing the denominator and I am changing the numerator 1 by 1, and if it turns out that the element is already there, I leave it out, okay. It is a very simple construction. Now, you give me any rational number between 0 and 1, you choose one, okay. I will find it in this set, right, whatever rational number you give me I can find it in this set, right. So, every rational number in 0 1, the interval 0 1 has a natural number index. I can speak of the ith rational number, correct. Is this clear? So, there are only as many rational numbers as in at least rational numbers in 0 1 as there are integers, correct. So, although there seems to be so many in 0 1, it actually is in bijection with natural numbers. Is that clear? So, you understood how I created this list. So, every time I increase the denominator and I go 1 by k, 2 by k and so on, and if that number is already there, leave it out. My claim is that this list that I have just completed, this is an infinite list of course, but this list has every rational number in 0 1. How do you prove that? You give me a rational number p by q, right, you reduce to its simplest form, okay, no common denominator etc. P by q, you go to the point where the q is in the denominator and check those guys, it will be there, right, because it will be there or it would have been covered earlier, right. If p by q is not in its simplest form, it would have been covered earlier, correct, that is it. So, every rational number is 0 1 is in this list. So, it is in bijection with n, correct, which means q intersection 0 1, the rationals in 0 1 is equicardinal with n, therefore countably infinite, okay.
Every element is there in that set,
Huh.
but where n is, we haven't touched n yet, right. Every element between 0 and 1 is there in the set.
So, this no, what I really mean by writing something in a list is that this is 1, this is 2, this is 3, this is bijection with, see, once you write the set down I can also write the set of natural numbers 1 2 3 dot dot dot.
But there should exist a function between them.
This is the bijection. So, with natural number 1 you associate 0, number 2 you associate 1, with 23 you associate the 23rd element, you know, that is it.
It is just index association, but there is no real function like.
This is the function. F of 1 is, so the function from n to this set is f of 1 is 0, f of 2 is 1, f of 3 is half, f of 4 is 1 by 3 and so on. That is the bijection. See, after all, what is a bijection with n? It is simply a listing of the set, right. N is 1 2 3 dot dot dot. Think of it as writing the names of students, right, 1 so and so, 2 so and so. You are essentially putting the set in a list, That is what a bijection with n really means after all, right. So, for every unique natural number, there is a unique rational number, and given any rational number I can find the index uniquely, right. So, it is the bijection. Is that clear? So, this is the bijection, it is not like I am just writing out the set. That is not true. That is what we are going to see.
Oh, that's not true.
So, rational numbers are special in the sense that although it looks like a very, I mean they are distributed all over the line, right. In any tiny interval of the real numbers you can find so many rational numbers, but there are only as many of them as there are natural numbers, they are countable. It is a very manageable set in that sense, right? There are only countably many rational numbers, right. It is not true. So, what is important, and it was realized first by Cantor, or at least proven first by Cantor, is that there are infinite sets which are truly bigger than natural numbers or integers or rational numbers. Okay. There are bigger infinities than simply the infinity of rational numbers. Okay. And those sets are called uncountable sets, uncountably infinite or just uncountable. Yes, uncountably infinite is a, it is a tautology, you do not have to say it, right. Uncountable sets are infinities which are bigger than natural numbers. Okay. Before we get there, I want to state a very important theorem without proof. Okay. Let I be a countable index set and let ai I belong to I be a collection of countable sets. So, this theorem I will not prove, it is a very important theorem. You can find the proof in Rudin or any analysis book. Okay. So, I am taking some index set, I is some index set, and this ai indexed by this I, this set is, these are all countable sets. Okay. Then the theorem says then union I belongs to I, ai is a countable set. Okay. So, in other words, so this is more glibly stated as a countable union of countable sets is countable. Right, this is a more colloquial way of stating the theorem. So, what am I saying? So, I am taking a bunch of countable sets, okay, and I am unioning all these countable sets, and the index set that I am unioning over is also a countable set. Okay. For example, this index set could be natural numbers or integers or even numbers or rational numbers even. Okay. And for each such index I have a countable set ai. Each of these ai's are countable. Okay. So, even if one of these ai's is not countable, this is not true. Okay. So, if each of these ai's is countable and I is a countable index set, then the union over I ai is also a countable set. Okay. Is that clear? So, which is countable union of countable sets is countable, that is what this is. Okay. Clear? This I will not prove. Okay. This requires a proof, but I will not prove it in class. Okay. You do not have to we do not have to spend time on this in class. Okay. But you have to know this result. Okay. So, using this theorem we can prove that the set of all rational numbers is countable. Why? Huh?
Each interval is
This can be a, see this, I have proven that the rationals in 0 1 is countable, it's a countable set. Similarly, rational numbers in any I comma I plus 1 is a countable set, right, and then I can write q as, so now I can write, so corollary, what is the corollary? Something that follows from a theorem, right, q is countable. Right, proof, you can write q as union I belongs to Z, union I belongs to Z, q intersection I comma I plus 1, right, correct. So, just like I argued for 0 1, you can argue that any I plus 1, the rationals in there are countable. In fact, you just add I to each of these guys, you have found a bijection. So, this is a countable set. Now, I am unioning over all integers, not necessarily positive integers, but integers, which is also a countable set, but this union is all of rational numbers. So, countable union of countable sets is countable. So, Q is a countable set. So, truly there are only as many rationals as there are natural numbers. Okay, so, that answers I think your question, right. So, if you union two countable sets, you always get countable set, as long as the number of sets you are unioning is also countable. Okay, is clear to everybody? Any questions at this point? Okay, so I think I just ran out of time, right. So, we have to continue next class.